Welcome back to ECE 501B. We are 1 week away from the last lecture. We have 3 more sessions together, including today's. We just have next week. Today, what I want to do is finish up the first textbook so that we have the rest of the semester to work on the second book. The second book will be in the final week, and that's Frank's text. So we've tried to pace it appropriately so that you have plenty of time to digest the entire Frank's book in the rest of the semester. Little tongue-in-cheek, but you now are prepared to start reading about infinite dimensional material in the second textbook. Homework number 8 is due tomorrow, and if you want to see me tomorrow, you'll need to hopefully adjust your schedule to accommodate this change. I think I announced this Monday anyway, but if you need to see me tomorrow in person, I should be in my office from 2 to 3. The project is due before we meet the next time. It's due Sunday. Teacher course evaluations are due in a week. Those are due essentially in a week and a few hours, less than 8 hours from now. I believe they're due at 11:59, and I would appreciate your input on those teacher course evaluations. Those results are reported to me right before I turn in your final exam grade. No, I'm teasing. Your grade will be posted long before I get to see any of this information, so you don't have to worry about your comments influencing your grade. Maybe next semester. No, but they're anonymous, and hopefully we have enough people respond so that I can see your responses. If we don't have enough people respond, then they don't let me see anything. So I need to see a fair amount of participation so that it is, in their sense, anonymous. Our final exam is less than 2 weeks away. It's on a Monday, the 15th of December, and it will begin a few minutes before we normally meet. It'll be at 3:30, and it will be a 2-hour exam. I think there will be about 8 problems in that 2 hours. Have we had 5 during 75 minutes? So now it's about the same amount of time per problem, and I need to post some material on D2L relative to the final. It probably won't be a practice final, but it will be a topical coverage and some review in terms of what you should expect to see on the final. Okay? And maybe I'll give you a little bit more, but how many sheets of notes have you had going into the first 3 sheets of notes, front and back? So you'll probably be given 4 sheets of notes, front and back is the idea for the final exam. As I said, today we will cover Chapter 10 material and a little bit more. We'll talk about the Moore-Penrose Pseudo-Inverse, which Penrose is one of the authors of one of the course resources, The Road to Reality, the chapters 2, 3, and 4, I believe. That's the author, or the second name on that inverse is the author of that material. And if you enjoyed reading that, then maybe you'll like seeing this pseudo-inverse that he essentially has created, or is obviously it has his name attached to it, or at least part of the pseudo-inverse title is his name. Then we will go over a little bit of principal component analysis. We probably won't get into functional analysis, which is the second textbook today. That's what we will do next week, but that's now infinite dimensional vector spaces. We've been worrying about finite dimensional vector spaces in this course so far, and we'll try to motivate that idea or that concept by means of the Fourier analysis. I'm thinking most everyone has seen Fourier analysis, and now you'll see these e to the j omega t's, and now you can think of those as vectors or eigenfunctions, like you think about eigenvectors. So we'll start talking about that on Monday of next week is the plan. Today what I want to do then is start with, whoa, what am I doing? I obviously had a different color the last time that was a gray color. That was kind of pale to me, or faint. So let me try a little different color, but I think I was writing on some figures and I needed more colors. But now chapter 10 of our textbook, and in particular, we want to cover the material that in the way that he does relative to the trace and determinant of operators or matrices. And so let's now look at this concept, or these concepts, trace and determinant of an operator. And in particular, now let's start with what we normally do. Let's say that we start with a vector space. If V, and now let's say that's is that a drugstore? CVS? A complex vector space. So V is not a drugstore, but it's a complex vector space. It's not a Walgreens. It's not a CVS. It's a C period V period S period, complex vector space. And T is an operator, a linear operator on that vector space. Then last time I think we talked about the characteristic polynomial. The characteristic polynomial of this linear operator T is written as a function of a complex scalar parameter z. Q of z is now z minus lambda sub 1 to the d sub 1, where these d's are the multiplicities of these eigenvalues. Z minus lambda sub 2, d sub 2, down to z minus lambda sub m, d sub m. What I want you to do is mentally multiply that out. Multiply that polynomial expression that's now factored into terms. Multiply it out, and maybe just do it for 2 terms with the d's 1. And what do you get as far as a polynomial? Let's say you have z minus lambda 1 times z minus lambda 2. Do you see what you get? You get a quadratic. And what do we know about this characteristic polynomial? We know that linear operator satisfies that characteristic polynomial by means of the Cayley-Hamilton theorem, but we can now replace the z's with the linear operator t. And if we do that in your second order, you would have q of t is equal to t squared minus what? So now I'm saying, here's sort of an aside. We were saying that we had q of z, just as an example. We had z minus lambda 1, z minus lambda 2. This now becomes z squared minus lambda 1 plus lambda 2 z plus lambda 1 lambda 2. Is that what you mentally saw when you were doing it? So you have a sum of all of these eigenvalues associated with the coefficient of lambda, or z to the n minus 1, or z to the 1 in this case, and then the last term, the constant term, is a product of all of those eigenvalues. If you do that with the higher order q of z, and if you now evaluate that for t, or at t, then this little q of z leads to little q of t equaling t to the n minus lambda 1 plus lambda 2 plus dot 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 plus, let's say, lambda sub n. Now I'm sort of going by number of n, so that includes the multiplicities, all of those n eigenvalues, t to the n minus 1, and we keep going, and then we might have a minus 1 to the n, but after that we have this product of eigenvalues. And that's consistent with this little example that we did that was second order. The first term post t to the n is just a sum of the eigenvalues, and the constant coefficient term is proportional to the product of these eigenvalues. This piece is really just called the trace of t, and this product is the determinant of t. And what we would like to be able to do is maybe find this characteristic polynomial a different way versus having to find it by building it up from this relationship. Meaning this relationship would say I need to compute all of my eigenvalues and find their multiplicities. Then I can multiply this polynomial out and replace the z's with t's. We want to derive another way of finding this expression that involves or is a function of the linear operator t. That's our goal. But once we've seen this expression, we can identify two pieces of that, two coefficients of that, and those are related to the trace and the determinant of this linear operator. That's where we're headed, is trying to find another way of finding this characteristic polynomial. For now, if I said, what's the trace? That's what I'm meaning by capital TR. I could write that in a shorthand way of just saying that's the sum of these different eigenvalues, all n of those, and it includes the multiplicities. But maybe we want another way of computing the trace of t without having to first find the eigenvalues. We know that the trace can be found by summing the eigenvalues, but is there another way to do that? And we can do that if we find a matrix representation of this linear operator t. If we have a matrix representation of t, then the trace of t is just the sum from I equal 1. Let's say that our matrix representation, this is an operator, so we know it's square. Let's just assume that it's little n or Nevada dimensional. Then we simply sum the diagonal elements in the matrix representation. That's how we would compute if we were just given the linear operator t without having to do the first step of evaluating the eigenvalues. We could find a matrix representation of t and then simply sum the diagonal elements along the dot of this matrix representation of t. And that would be equal to the sum of the eigenvalues of that operator. And we wouldn't have to go through that. So here are some matrix facts that I'm essentially sort of giving you. if you haven't seen them. The trace of a matrix A is just the sum from I equal 1 to n of the diagonal entries, A sub I, that's what I'm meaning, the ith row in the ith column, and that's equivalent to the sum of the eigenvalues. Let's say from lambda sub L equal from, or the sum from little l equal 1 to n of lambda sub L. Yes? So this is valid even when the matrix is not upper triangular. So the question was, okay, I can see that this relationship is true when it's upper triangular because my diagonals are on the, or my eigenvalues are on the diagonal. But this is true even if your matrix is not diagonalized or upper triangular. The trace of the matrix is defined to be just the sum of the diagonal entries, and that will actually be equal to the sum of the eigenvalues. Okay? The determinant of a matrix, which we may denote as A with vertical bars on either side, or we might say just the determinant of A, that's now equal to this product of eigenvalues with multiplicities included. And for this linear operator T, the determinant of T, again maybe calling it det of T, is the constant term in the characteristic polynomial times minus 1 raised to the dimension of your vector space V. So if you wanted to compute it, if you could find your characteristic polynomial or write it out, then all you would really need to know is what's my constant term in that, and that's now going to be my determinant of this linear operator T. And even if we have this linear operator on a complex field, the determinant of T is still just the product of these complex eigenvalues. Now, if you know something about the determinant, you can also say something about the operator's invertibility. Here's a proposition. An operator is invertible if and only if the determinant of that operator is not equal to 0. And that's related to what we've just been working with above. We said, well, remember when an operator is invertible or non-invertible. Remember, an operator is non-invertible if and only if it has a 0 for an eigenvalue. We've learned that from before in terms of some of our propositions relative to invertibility, or a matrix being injective or surjective. Now, an operator is non-invertible. We can't invert it if it has a 0 for an eigenvalue. Now we know that in both complex and real, in both the complex and the real case, the determinant of T involves a product of eigenvalues. Which now says that if the determinant of T is equal to 0, that's only going to happen, or the determinant of T is equal to 0 if and only if there exists a lambda that's 0, and that's then going to give us a product of these eigenvalues equal to 0, which is what we were claiming. We said an operator is invertible if and only if the determinant is non-zero. And it could be negative, your determinant. It doesn't have to be non-negative. Now, what we said before was we wanted to see if there was another way to try to find this, or to perform this determinant of T, or to find this characteristic polynomial without doing this, finding the eigenvalues, finding their multiplicities, multiplying out this polynomial, and then replacing all the z's with t's. Can we do it another way? And that's where we want to go now. To do that, then, let's realize or make the following observation. Note, for a linear operator T with lambda and z belonging to the field of numbers, then lambda is an eigenvalue of the linear operator T. That double-headed arrow is just a shorthand for if and only if z minus lambda is an eigenvalue of another operator, zi minus t, which is a related operator. But if we know that lambda is an eigenvalue of t, then we know also that z minus lambda is an eigenvalue of the operator zi minus t. And again, we will use this fact to find another way of coming up with the characteristic polynomial. So there is basically a fact, and if we put our 2-year-old cap on, we might say, why? Why is that true? Why, if lambda is an eigenvalue of t, are we assured that z minus lambda is an eigenvalue of zi minus t? And we can show that pretty easily. Suppose that we now start with zv minus tv. Let's just take that algebraic expression. We can force the identity operator in between the the scalar and the vector v without changing anything. So we can say ziv minus tv. But we can also say that if v is an eigenvector of t, let's say with eigenvalue lambda, we can rewrite tv as lambda v. Okay? So this is true if we assume that V is an eigenvector of T. The other thing that we can do is we don't have to have this identity operator there on the right, so that now the right is just two scalars, z and lambda, scaling the same vector. And we can factor that vector out on the right-hand side. We can say z minus lambda times v. But over here on the left, we can factor a vector out of those operators, zi and t, so that we now have zi minus t v. And what does this resulting equation look like? We have a vector that's invariant to this operator because it's just a scalar multiple of that same vector. And that's our eigenvalue eigenvector equation. This is our eigenvalue eigenvector equation, which now says that if V is an eigenvector of T, then if lambda is an eigenvalue of T, then Z minus lambda, which is this piece right here, is indeed an eigenvalue of this operator Z minus T, Zi minus T. So we can make that conclusion, and that's assuming then that if V is an eigenvector of T. So now whenever lambda is an eigenvalue of the operator T, then we know that Zi minus lambda is likewise an eigenvalue of this new operator Z capital I minus capital T. That result then, right here, Zi minus lambda being an eigenvalue of this new operator, Zi minus T, is going to allow us to remember what we could do about the determinant of an operator. The determinant of an operator was just the product of the eigenvalues. Now let's look at the determinant of this new operator, Zi minus T. Now that we've convinced ourselves with our y question, this result lets us compute what we wanted, the characteristic polynomial of T, without having to compute eigenvalues and then form that product via the following theorem, where the theorem now is as follows. If T is a linear operator on V, the characteristic polynomial of T actually equals the determinant of Zi minus T. So now we can find the determinant of, or the characteristic polynomial we can create if we just compute the determinant of Zi minus T. And where did that come from? Well, that's just using the above relationship. Remember, from before, the determinant of T was just the product of the eigenvalues of T. Let's say they're the eigenvalues of A, which is the matrix representation of T. If we know that if we have an operator, we know now that the determinant of that operator is just a product of the eigenvalues. So what if we want the determinant of Zi minus T? Well, now we know the eigenvalues of Zi minus T are just Z minus lambda. And we know all of the lambdas, lambda sub 1, lambda sub 2, all of those lambda sub i's. So we can now say that the determinant of Zi minus T is the product of Z minus lambda sub I from I equal 1 to n. But that's just this product, Z minus lambda 1, Z minus lambda 2, etc., Z minus lambda sub n, and that's what we were setting out to show, that the determinant of the operator Zi minus T is the characteristic polynomial, which is what we have here on the right-hand side. So instead of having to compute the eigenvalues of this linear operator, we can simply find the characteristic polynomial from the determinant of Zi minus T. And that's going to be a function of this scalar parameter Z. So now you know how to find the trace and the determinant of a linear operator. Let's now move on and say, let's look at some of these other concepts. One was the Moore-Penrose pseudo-inverse, and the other was the principal component analysis. Those were our goals for today. Let's now look at the Moore-Penrose pseudo-inverse. And remember, this Penrose is the person that penned the road to reality that we had a couple of chapters on in our course resources. Here's the way we want to talk about this pseudo-inverse. Suppose you have a map, and on that map is a continent, or no, we're talking about maps in a vector space, not in geography class, although if you step out of these doors, you're going to see a lot of maps, aren't you? That's the building that we are in. That's not the kind of map we're referring to, but now we're talking about maps between vector spaces, and this map could be a measurement system. It's another way of thinking of a map. Now you have some quantity you want to measure, and you have an instrument that senses some signal. You want to know, how do I relate this measurement to the signal? So here is our map, and let's say T is a map between let me use the right letters, between U and V. And we could then view that as M is equal to TW in, let's say, now it's sort of a shorthand. T is now this matrix represent, well, M and W could be vectors. Let's say now with W living in U, where U is a finite dimensional vector space, let's just give us some numbers to keep track of. Let's say this is a finite dimensional vector space of dimension capital N, and let's say little m, which is a vector in the codomain capital V. Let's say that that dimension of the codomain is capital M. And now what we want to do is we want to say that we can measure M, and we would like to know what's W. Or we have available M, what is W? We're trying to basically find W by measuring M. And there's many different ways that this could present itself in terms of a lot of different possibilities or combinations of these dimensions, little or capital N and capital M. So what we want to do is we want, or we wish, to use output vector M to infer or learn something about the input vector, where the input vector is W. Or another way of maybe thinking about that is, what is the best linear method for estimating this input vector W from the output vector M? And I might use the following notation. I might use a hat to mean the estimate of the input vector. So let me say that I'm going to define W hat to be the estimate of the true input vector W. So now, here's our question. What is the best linear method for estimating the input vector W from M, where M and W are related by this linear map T? So now we want to basically find the inverse of T, and we want to know, does the inverse of T exist? And if it doesn't, how do we find the best linear way of creating W hat? So the ideal would be, oh, let's just invert this linear map to find W. And that's the first answer. Answer 1, let's say A sub 1, says if U is equal to V, those were the two vector spaces, the input vector space and the output vector space. If they are the same or they're equal and T is a linear map that is actually full rank. We've talked about full rank. Yes? No? Full rank means that this is now a square operator, isn't it? Full rank means that we essentially have a non-negative or a non-zero determinant is one way of thinking of it. We have full, or we have linear. If this linear map T was represented as a matrix, all of our columns would be linearly independent, or all of our rows would be linearly independent. That means it's full rank. That's what we mean by full rank. Or you could think of that as saying I have a non-zero determinant. If that's the case, if T is this linear operator that's full rank, then the best estimate is, in fact, exact. Meaning, if we now take and try to find omega sub hat as the inverse, then if T is full rank, it does have an inverse. That means it's surjective and injective. Then we can find its inverse. And what was M? M was just TW, so that now we have T inverse TW. That was essentially the definition of M, T, and W. But now T inverse, since it exists, operating on T, says that now W hat, our estimate, is in fact equal to W, which is the true input vector. That's if our linear map is full. What we want to do is look at some cases that are not so ideal. Suppose we look at another answer, A sub 2. Suppose, though, that U and V are still the same, but now let's drop this full rank assumption. Suppose T is still a linear operator on U or V, they're equal, but now it's not full rank. Or what's another way of thinking of that? Remember, in this picture that I'm drawing, here let's say is U and here's V. They're the same. Those are the same vector spaces. And we are mapping between the vector space in itself, or from U to V with T. But now, since T is not full rank, we might have a lot of vectors in U that map to the same point in our vector space V. Meaning T is many to one, or many vectors. That's what those clouds are supposed to mean inside the bigger cloud. That smaller cloud is a bunch of vectors. We might have many vectors that map to the same vector, which really means that that's non-injective, or that means we have a non-trivial null space. And we can now pull a lot of vectors from that null space and add those to other vectors and get to the same point in our codomain. So T being many to one means that our map is non-injective, which now says that we do not have an inverse for this map. So if that's the case, if it's many to one, let's have another question. Let's say Q prime. If we have several estimates for W, which we might be calling W sub hat, which W sub hat do we use? Which of many possible W sub hats should we pick? W hat is a vector, and we've talked about the norms of vectors. That gives us something about the length. Why don't we just pick the W hat that has the smallest length and say that's the best estimate of this W vector, the input vector. So let's now just say that our answer for Q prime is A prime. Pick the one of maybe many possible estimates for W. Pick the one with the minimum norm. Now we can show that, or we can see that the same thing happens in terms of many to one if capital M, which is our dimension, let's go back to where we had defined those. Capital M was the dimension of our output vector. If little m, that vector, is shorter than W, then T is short and wide as a matrix, if you viewed T as a matrix. And if it's short and wide, then it has a non-trivial null space. So the same thing happens in terms of its many to one. If our codomain vector space, capital M's the dimension of that, capital M, is less than the domain's dimension, which is capital M. Because this is also many to one and non-invertible. Or you might hear this referred to as underdetermined. And if that's the case, we would still want to find the W sub hat that's the minimum norm. So again, seek to find minimum norm solution. So before we find this minimum norm solution, let's just see that we need it also for the other case. If the matrix representation of T is now tall and narrow, or M is bigger than N, then the system is not underdetermined, it's overdetermined. We have more equations than we have unknowns, so our system is overdetermined. Which says a unique solution should exist but now this matrix representation of T, like I said, is tall and narrow, so it's not square. And it would be nice to find how to find an inverse. So all of these that are underdetermined, overdetermined, we can address using the same approach. So all situations can be addressed by finding a reconstruction operator P that actually minimizes the error. Where our error let's just define as the norm of t w hat minus n. So we're trying to find a w hat that minimizes this norm, or the square of this norm. And you know how to start sort of building up an expression for the norm squared. What's the norm squared equal to? Inner product of that expression, tw hat minus n, with itself. And you can start moving operators between different slots. And if you do all of that, you can show that if you now look at the partial derivative of E with respect to w hat, again, we're trying to minimize a quantity, and now that says, oh, calculus, let's set the derivative equal to 0. You can show, if you look at this by means of its inner product and pull all of those pieces together and then start differentiating with respect to the unknown vector, or the estimate, w hat, this will be equal to 2 times t dagger, which is the adjoint of t, times t w hat minus n. So going through that inner product, shifting things around, you can now find that you're going to have this w hat transpose t dagger t, etc. You take the derivative, and now we want to minimize that, which says that we can set that equal to 0. Setting that equal to 0, the 2 is a non-zero value, so we can multiply both sides through by 1/2 without changing that expression. We now have t dagger t w hat minus t dagger m equaling 0. Push the t dagger m to the other side. And now t dagger t is invertible, so that we can solve for w hat, and w hat now becomes t dagger t inverse t dagger m, and this operator p, which is now t dagger t inverse t dagger, is the Moore-Penrose pseudo-inverse. So now we have an expression for this Moore-Penrose, and that's doing what? It's basically picking the estimate of our input vector that has the smallest norm. That's what we have. That's how we've derived this Moore-Penrose pseudo-inverse. Here are some observations or notes relative to this pseudo-inverse. One, if it turns out that t dagger t is not invertible, it's always going to be square. We know that. T adjoint t is square. We can actually show that if we define p to be the limit, let's say as epsilon goes to 0, of t dagger t plus epsilon I inverse t dagger. That operator always exists and it does minimize the error. And what do you know about epsilon I in terms of its rank, or how full is it in terms of, if you looked at the columns of the identity matrix, how are they related, or what's their dependency? They're all linearly independent, aren't they? So now we are adding in a positive term to T dagger T that may not be invertible, and letting epsilon go to 0, we will then be able to invert that operator in the parentheses. And then we can apply that P. Here's the note that I like maybe best, and that is that P can, let me say, can be easily obtained from the singular value decomposition. So let's now say that our matrix representation of our linear operator, so I'm sort of abusing notation. Let's say T is U sigma, which I'm representing as S, V transpose. That we've talked about. That's our singular value decomposition. If that's the singular value decomposition of our matrix representation of T, then our inverting map, P, or the pseudo-inverse, is now V S tilde U transpose. Remember, the vectors of U and V are orthonormal, and all we're asking is to transpose the columns in U into rows and generate some S tilde. And what is S tilde? Well, suppose that S in our singular value decomposition is a diagonal matrix with S sub i's on the diagonal. That's the definition of the singular value decomposition. Now, some of those, if T is not full rank, then some of those S sub i's will be 0. And that's why we have to not say S inverse, we're saying S tilde. Here, we're going to say S tilde is diagonal, just like S is, but now along its diagonal, we will replace the diagonal entries with 1 over S sub I. That's only if the S sub i's are non-zero. If we do have a a 0 S sub I, then we set that equal to 0. We don't try to divide by 0, in other words. That now gives us this pseudo-inverse, P, in terms of a linear map. So singular value decomposition to the rescue is another way of thinking of that. The third note is, if in fact T is invertible, then P actually defaults to the inverse of T. P was defined to be T dagger T inverse times T dagger. But if T is invertible, we can actually invert T dagger T, and if we have an inverse of a product, we simply reverse, or we exchange the order of the product of those terms, meaning now we have T inverse and we have T dagger inverse, all times T dagger. But what is T dagger inverse T dagger? That's just the identity, and we now have T inverse. Here is just the identity, and that's now just the inverse of t. So this pseudo-inverse actually works in all cases. And it looks like my computer is not working in all cases. Wow. And I don't like the way that looks. That looks like I've lost all of OneNote. So let me now what I want to do is actually start talking about principal component analysis, if I have any time to do that. Now, I don't like what that looks like, so let me just continue on a new page and say, here, let's talk about, wow, it's going to default to my pen from before. Let's now look at the principal component analysis. So now here is our question. Question 1. Suppose we're given a set of vectors. We'll call that set of vectors S in a finite dimensional vector space V where the dimension of V is n. What we are interested in is this question. What is the shortest list? This is now a list of vectors that can represent a vector x in S. And typically you can get by with an answer that says it depends, right? Most of your answers you can say it depends. Well, this actually depends on what S is. Here are some examples. Suppose that we start with our underlying vector space V being R2, and suppose that S is really any vector in R2, and we want to know how do we represent, or what's the shortest list of vectors needed to represent any vector in S. Or we're saying we have a two-dimensional vector space, let's say x1 and x sub 2, and now we have some generic vector x. How many, so for this arbitrary vector, in R2, how many vectors in our list do we need in order to represent that blue x? we need a list of how many vectors? 2. So now we need to look at our list being the same dimension as V, since S is that dimension. So that one is fairly clean to understand. What if we start with our underlying vector space being R2, and S now is the x1 axis. So again, we have this two-dimensional vector space, but now somebody's giving us vectors that are only in the x direction or the x1 direction. How many vectors do we need in this list to sort of span or be able to represent S? 1. So now we only need, let's say, one number, since now we could be saying, oh, just give me A, where the vector S in A, I'm sorry, the vector in S is just something 0. It's always on the X. All you have to give me is that something, and I'll know where you're at in S. Here's another situation for S, still playing in R2. Suppose now that somebody says, oh, I now have in x1 and x sub 2, or in R2, I have let's say these dots, you could draw vectors from the origin to those dots, and those are now the vectors in S. Or now, and S is clustered around what? Maybe it's clustered around sort of this line, x equal y, or x sub 1 equal x sub 2. Can we actually describe that with a list that's maybe shorter than 2 by knowing this one-dimensional vector, that x1 is equal to x2? In general, there may not be a perfect short list, but what if we are interested in the best short list of some size? And this becomes more interesting if we have vectors in more than 2 dimensions. Maybe it's in 30 dimensions. So this is a more interesting problem in higher dimensions, which is really saying we have a second question. In what basis do we obtain the best k-dimensional approximation to a vector x for all possible k's less than or equal to n, where n was our, in this discussion, that was the dimension of our underlying vector space. In this case, our answer, a sub 2, is that principal component basis is our answer. And that's also called the Karhunen-Lev basis, or KL basis for short. So what we want to do is we actually want to find an orthonormal basis let's say B, that will allow us to minimize the expected value of the norm of x minus x hat squared. That's what we want to do. So now if we have an orthonormal basis, we can start a decomposition of any vector x in those directions or in those bases by the appropriate inner products. We could say x is x inner product with b1. That's the component of x in the direction of b1, so let's let x b1's inner product weight b1, and b1 is an orthonormal basis vector. And we can continue to do that. And remember, we said that we had a finite dimensional vector space, so in theory we can keep doing this out to the final n, and there is now our decomposition of the beginning vector x. We now want to know how can we select an x hat that doesn't have all of those basis vectors, little n. Maybe it has 2 or 4 or 5. How do we select those? Well, we can now just make x hat be x b1 up to the appropriate k that we want to pick, since these are orthonormal. And now we just have to figure out how to pick b1, b2, etc. How do we pick these orthonormal basis vectors such that x hat is the best approximation that minimizes this distance between x and x hat? So we're saying now that we want to build up x hat out of these orthonormal bases where now p is less than n, and we want to be able to build that up no matter what p we select. Maybe we select p equal to 1. Suppose we do that to begin with. Suppose or consider the case when p is equal to 1. Then x hat, by definition, is simply x b1 times b1. But now what is the norm, the expected norm of x minus x hat squared? Well, x hat is now x b1 times b1, and we're removing that from x. And if we look at x minus x hat, the only thing that's going to be left is the tail on x from b2 up to b sub n. So that now we can say that this is equal to the expected value of this sum from I equal 2 to n of x b sub I. Remember, the b's were orthonormal, so we don't have to worry about that. We just need to square the coefficients. And now to minimize x minus x hat, it would be nice to do what? we want to make B1, or this inner product of x with B1, as big as possible to make this as small as possible. So we want to pick the B1 to be the biggest relative to how it correlates with x. And that's the principal component. I'll probably have to add on to this later, since I hear the next class wanting to get in, and we'll start with the next textbook on Monday, and I'll try to give you some more information on principal component after this, in addition to what we've just started. But now think about what you have relative to x and x hat, and what results when you look at their difference, and if you now start moving up in terms of values of p. 1, 2, and just look at the first case, you can see that you now want this inner product of x b1 to be the largest piece in order to make this sum on the right as small as possible. And we'll pick up with that in another time.